So as I said, this particular section is new to the the AB curriculum, just the last few years, but it's a really simple idea. But involves, and appropriately so, involves the limit concept. And so wearing the shirt today was helpful. And in subsequent years, nobody will have any idea what I'm talking about. So, L'Hopital's rule. And the key thing is recognizing when you should do that. The questions where you would see this would absolutely be a multiple choice kind of a question. And it's typically a quick little process that you have to do. But sometimes the hardest part is recognizing when to use that. So, if the question is something about, what's going on near 1, recognizing that that's a limit question. That if I have the natural log of x over x minus 1, what's going on near 1 is simply saying what's the limit as x approaches 1. Remember, this, of course, is a two-sided limit. It's plus and minus coming from both sides of that. And, of course, the way you find a limit is to simply take the number and plug it in, if possible. Well, I took a look at the graph of this thing. So I graphed that, and it ends up looking something like that. And so you can tell by looking at the picture, there appears to be, at 1, there appears to be some kind of an answer. There appears to be a limit. But when I plug in 1, now remember the natural log, looks like this. So at 1, it's equal to 0. And I plug 1 into this, and I get 0. And what I get is 0 over 0. And I cannot say that 0 divided by 0 is 1. That's not a true thing. So, but as we said, clearly there appears to be a limit. This function appears to be approaching something. So how do you do this? So a general form of this, when I'm taking a limit, some function divided by some other function. If the numerator is approaching 0 and the denominator is approaching 0 as x approaches a, then, and here comes the key phrase, then it may or may not have a limit. The limit may or may not exist. This is what's called an indeterminate form. You cannot determine what the limit is the way it is, because you get 0 over 0. So, sometimes, like I said, what you can do is just try to plug in the number. Plugging in the number in this case doesn't work in this example. I'll come back to that other one in a second. But sometimes we have techniques, and here's the thing, recognizing when you should use L'Hopital's rule and when you shouldn't. When you have a problem like this and you try to plug in the number and I end up with 0 over 0, you can deal with this one sometimes, and these are the simple kinds of questions early on in the multiple choice. You should recognize that you can factor that. And when you factor out the x and you factor the difference of squares in the denominator and the x minus 1s cancel, now I can plug 1 into there and get 1/2. So even though at the beginning plugging in the number gave me 0 over 0, I don't have to do anything fancy for that. We learned about that kind of limit way, way, way back. All right. Sure. So going back a couple slides, this indeterminate form or type is just simply saying when you plug the number in, you don't get an answer. You get like 0 over 0. And so if it is 0 over 0, it may or may not exist. But this process, this L'Hopital's rule, will help us figure out whether it exists or not. So, okay, so we tried plugging in 1 in this one. It didn't work, but we realized, okay, you can factor, and that is a tool that works. Where are you? Sorry. It just factors, right? And that's all I'm showing. Okay. I'll catch that with you in a second. Sometimes you can, if your calculator active, if you got your calculator with you and it's asking about a limit, just graph it. Now, again, if I take 0 and I plug it in the sign of 0 is 0. Take 0 and plug it into there, you get 0. And by golly, you get 0 over 0. So that's that indeterminate type. But graph that on your calculator, and look what it looks like. Put it into radians, and graph that thing. And you should be able to tell by looking at the picture what the limit is. Even though it's undefined at 0, the function is equal to, or becomes closer to, 1. So the limit of that is 1. So a variation on a theme. So in this case, I had, when I plugged in 0, I got 0 over 0, can't tell. But the actual limit is 1.
So there, 0 over 0 does equal 1.
Well, 0 over 0 doesn't equal 1, but the limit is 1.
Okay.
The value the function approaches is 1. Variation on a theme. So a moment ago, I had this sentence, and I said if f of x, is approaching 0, and g of x is approaching 0, then you get that indeterminate type of 0 over 0. But the same thing can be true if these two things both approach infinity. So you've got this fraction. And the problem here, of course, that we're running into is it ends up being division by 0 in the last problem. And in this case, it's going to end up being division by infinity. So, exact same sentence as before, just change the zeros to infinities. So an example of that, and so again, indeterminate type, but this time infinity over infinity. So same phrase as before, but instead of being an indeterminate type of 0 over 0, it's an indeterminate type of infinity over infinity. And it may or may not exist. Okay, so here's actually L'Hopital's rule. If f and g are differentiable, so you've got functions in a function in the numerator, a function in the denominator. They're differentiable. I can take their derivative. The derivative is not in the denominator, can't equal 0.
Can't be constant.
Right. On any interval containing a. So the derivative can at some point can be equal to 0, possibly at a, but not everywhere. So here's the actual rule. Nope, not the actual rule yet. Sorry, I was ahead of myself. So what this is saying is that if the numerator as x approaches a, the limit is 0, and the denominator as x approaches a is 0, and that was that indeterminate type of 0 over 0, or if the numerator is approaching positive or negative infinity and the denominator is approaching positive or negative infinity, in other words, if it ends up looking like that, then you can apply L'Hopital's rule. So a prerequisite for this, when I ask this for you on a test question, is you need to first determine whether one of those two things is true before you apply it. So step one always is, does L'Hopital's rule apply? All right, I'm finally getting there. Yay. I was ahead of myself. Say again? Yeah. So this is what this says. If you have L'Hopital's premise satisfied, 0 over 0 or infinity over infinity, then you can apply the rule. And the rule just simply says that the limit of this that gave me 0 over 0 or infinity over infinity is going to be the same if I take the derivative of those and then find the limit. So there's a lot of problems that we previously couldn't find the limit for that now suddenly you can. Now, The only thing that's calculus about this is having to actually take the derivative, but it's really, the limit is mostly, we started doing limits back in pre-calc. So the only reason this is a calculus question is being able to do the derivatives of each of these guys. All right. If it exists, yeah. So you've got to be able to take the derivative, remember?
Do you take the derivative of the whole thing using the quotient rule? Or
No, just the individual ones. And that's an excellent question, because that can be confusing for some. Because you're looking at it thinking it's a quotient, but it's just the derivative of the numerator and the derivative of the denominator, not the quotient rule. Right. You're not taking the derivative of this. You're taking the derivative of the numerator and the derivative of the denominator. You're right. This derivative of that would be a quotient rule. This is also, don't write this down. This is also true for one-sided limits. So if you're coming just from one side or the other, you can still apply this kind of logic. All right, so back to this problem we had at the beginning. This natural log of x over x minus 1 as x approaches 0. We saw from the graph that the limit appeared to exist. The graph sure looks like it's getting closer and closer to some value. But when we plugged in 1, we got 0 over 0. So what L'Hopital's rule says, so when I plugged in 1 into this, I got the demonstration that this was 0 over 0. So that's what says that I'm allowed to apply this, that L'Hopital's rule fits this situation. So let me do derivatives of each of them. So the derivative of the natural log of x is 1 over x. And then the derivative of x minus 1 is 1. Now take the derivative. Sorry, try that again. Now take the limit. Plug in 1 into this equation. You get 1 over 1. And plug in 1 in the denominator. Well, there's no place to plug it in. You just get 1. And sure enough, 1. Huh. Look at that. Another example. So, find the limit as x approaches infinity. Okay. So as x goes to infinity, e to the x goes to, well, e to the x, of course, looks like this. So as x goes to infinity, y is going to infinity. And, of course, as x gets bigger and bigger, x squared also goes to infinity. So I got infinity over infinity. Aha! L'Hopital's rule. It's infinity over infinity, which I cannot figure out what that is as it is. So what I'm going to do is take a derivative on the numerator and in the denominator. And then I do the limit again. And I end up with e to the x over 2x. And as x goes to infinity, I get infinity over infinity, to which you say,
Do it again.
Do it again.
I don't think it's going to work.
And so now, I get e to the x over 2, but it's not infinity over infinity. So as x goes to infinity,
It doesn't exist.
this... Now, so, does this limit exist? Technically, no. But the way in which it doesn't exist is it's approaching infinity. So you remember that idea of infinity is not a number, so I can't, the limit is not, it's not a number I'm approaching. So the limit doesn't exist. But this is just simply e to the x divided by 2, which is just that, just a little bit shorter. And as x goes to infinity, that goes to infinity.
So if it didn't work, do you want us to just keep taking the derivative of it?
Eventually, one of two, you'll get something like this in most cases, where eventually something just kind of stops. I can't go again because I have to with 0 in the denominator, so I can't do it anymore. But usually, what happens is after one or two times, it'll work. you'll be able to figure something out. So another example. Find the limit. Well, as x goes to infinity, natural log's going to infinity. Natural log, of course, looks like that. And cubed root of x looks like that. And as x goes to infinity, it also goes to infinity. So the numerator, as x goes to infinity, the numerator is going to infinity. And as x goes to infinity, the denominator is going to infinity. So I got infinity over infinity. The rule applies. Rule says derivative of the numerator, derivative of the denominator. Take each one. Derivative of natural log, 1 over x. Derivative of the denominator, keep in mind it's x to the 1/3, so 1/3 x to the negative 2/3. Ooh! Simplify first. Always, always. So I'm going to make that thing become that. Now, take that limit. So, right? This negative exponent comes up. This in the denominator becomes x to the negative 1. Add the exponents. You end up with negative 1/3. Put that back in the denominator. Take that limit. And now as x goes to infinity, right? Like, for example, this, as x goes to infinity, 1 over x is going to 0 on my t-shirt. Huh.
Where did the 3 on the top?
Oops. That guy became that guy in the numerator. Dividing by 1/3 is the same as multiplying by 3.
Where did the
Squared go? Right there. Sorry, thanks. So, let's think about this one for a second. Plugging in pi. Sine of pi? 0. Cosine of pi. What's the cosine of pi?
1.
Negative 1.
Oh, yeah.
No, 0. Cosine CX. No, negative 1. Right. Hold on, let me come back. Cosine of pi, cosine's the x value. Pi's out here. X value is negative 1.
0 over 2.
Yeah, hold on a second here. So, here's what happens when you shouldn't apply L'Hopital's. I lost track of where I was in my notes here. So we kind of glance at this and think, oh, some division thing. Let me do L'Hopital's rule. So I do the derivative. Derivative of the sine is the cosine. Derivative of that is derivative of cosine is negative sine, but minus cosine is positive sine. Great. So limit as x goes to pi. As x goes to pi, this is approaching negative 1, and this is getting closer and closer to 0. As the denominator of a fraction gets closer and closer to 0, the fraction gets closer and closer to infinity, right? When the denominator gets small, the fraction gets big. So you would think that this is going to negative infinity. But, where was that? Sorry. There it is. But when I graphed this original thing, it looks like this, and it appears, sure enough, it's going to some value. And what happened was, when you just plug pi in, as we saw a second ago, sure enough, I don't get 0 over 0. I get 0 over 2, and that's 0. So it can be, if you apply it in a situation where it shouldn't apply, you're going to get a wrong answer sometimes, or possibly. That's the only point of that. Okay? So, step number 1 always is verify that you got 0 over 0 or infinity over infinity. Okay, variation on a theme. And this is the kind of problem that I think you'll see. They do this to you a lot. They'll give, so a fun fact you're supposed to know from, I don't know, pre-algebra somewhere. F times G is the same thing as F divided by 1 over G, or G divided by 1 over F. As we were talking about a minute ago, division by a fraction, same thing as multiplying by the reciprocal. So, when you have a problem like this, it doesn't look like it would fit the L'Hopital's rule because you've got a multiplication and everything we had was a division, right? 0 over 0 or infinity over infinity, neither of which disappears. But I can rewrite this. Well, when I try to plug it in, I get 0 times negative infinity, which just doesn't make sense. And so that didn't work. But when I do think of x as dividing by 1 over x, and now when I plug in 0, as I get closer and closer to 0 from the right, natural log goes to negative infinity, and this would go to positive infinity. As x goes to 0, right, this is going to positive infinity, so I got an infinity over infinity. So L'Hopital's rule applies. I can take each one of them and do a derivative. So derivative of natural log is 1 over x. 1 over x is x to the negative 1, and then the derivative of that is negative 1 over x squared. Do a little simplifying, probably. Bring this up into the numerator, right? Because it's 1 over x squared, so it's just x squared in the numerator. This x will cancel out with one of those and just leave x. Now, let x go to 0, and I actually get 0 as an answer then. So the limit is 0. You take a deep breath there. So the trick of what this particular example was about is recognizing, even though that's not a quotient, I can rearrange it and make it a quotient, and then apply L'Hopital's rule to it. All right, so way back at the beginning, we had this one where it was, when you plugged in 1, you got 0 over 0, but the easier way to do that was to do it by factoring. And we factored out the x, and we had the x minus 1, and x minus 1, and x plus 1. But, just for giggles and kicks, I'm going to do it with L'Hopital's rule. So, take the derivative of the numerator, that's that. Take the derivative of the denominator, that's that. Now, plug in the 1. So, 2 times 1 is 2, minus 1 is 1, and plug in 1, you get 2, and sure enough, you get the same answer. So it's not wrong to do it that way, it's just a whole lot harder. It's a lot easier just to recognize that that factors and cancel out the common factor. One last one. So the limit of the secant of x minus the tangent of x. So remember what the secant looks like. Remember the secant is the reciprocal of the cosine. So here's the cosine curve up here, and then the reciprocal of it looks like that. And as I'm approaching pi over 2, you're approaching infinity. And the tangent of x is looks like this, and as you approach pi over 2, it goes that way. But this is not a quotient to which you would not necessarily apply L'Hopital's rule. But after doing a little bit of rearranging, recognizing that the secant is 1 over cosine, the tangent is sine over cosine, I can write that now as one fraction. And now when I plug in pi over 2, the sine of pi over 2 is 1. So when I plug pi over 2 into that, I get 1 minus 1 or 0. And then when I plug in pi over 2 for cosine, cosine of pi over 2 is also 0. So this is 0 over 0. So L'Hopital's applies. And you need to verify that first. So it's not an obvious problem that you should do that. So what I'm trying to give you here is a little bit of the variations on a theme. So derivatives. Derivative of 1 minus sine is negative cosine. Derivative of cosine is negative sine. Now when you plug in pi over 2, cosine of pi over 2 is 0, and then the sine of pi over 2 is 1, so it's negative 1, so 0 over negative 1, 0. That's it. That's the logic of L'Hopital's. And those are the kinds of questions that, those last few, I think, are the possible kinds of questions you would see on multiple choice. So, this would be a good example out of that homework to try.